Let me remind you where we left off yesterday. Yesterday we introduced what Landau levels were. We solved the single particle problem, i.e. a single electron in a perpendicular magnetic field in the Landau gauge. A vector is and we discovered that it was just the harmonic oscillator in disguise, and that told us exactly what the energy spectrum was. So we plotted that the energy versus K was flat. These were the Landau levels. This spacing was set by the cyclotron frequency. We then worked out what the degeneracy of each Landau level was, which we denoted by n phi. We said that this is equal to the total flux piercing the two-dimensional surface divided by the flux quantum. We noted that it was extensive in the in the area of the system. And then within the Landau gauge, we drew a picture for what the wave function looks like, which was that it has a Gaussian profile in the x direction, localized around a center point xk, which is, let me write it here, xk, which was minus k lb squared. So I don't know if I stressed this yesterday, but note that the position in the x along the x direction is fixed by the y momentum. Okay, now this is going to be, we're now going to explain the quantum Hall effect, which is what we set out to do yesterday, and this is going to be key. The position in the x direction is set by the y momentum. Okay, and so along the x direction, it has a Gaussian profile around this center, and in the y direction, it had uniform amplitude. Right, so we saw this yesterday, and now, using all these pieces of information, let's explain the Hall effect. What do we want to explain? We want to explain the fact that the current in the y direction is related to the electric field in the x direction. That's the signature that we want to explain. And in particular, this is x, y. Nu e squared over h, where this nu is an integer, and nu indicates the filling of the single particle spectrum, which is that nu is the number of electrons divided by the degeneracy of each Landau level. Okay, so nu is known as a filling factor, and it tells you how many of these Landau levels are filled once we take. Because remember, we solved the problem for a single electron, and we're trying to describe a system with some large number of electrons. And we had a density of electrons, something like 10 to the power 22 per centimeter cube, something like that. And so, as usual, just like we've done before with band theory, what we do is we fill the states in this spectrum. And mu tells you how many of these Landau levels are filled. So to start with, we're going to work with this quantity is an integer. Okay, so if only this lowest Landau level is filled, there are exactly n phi electrons in the system, and the filling factor is 1. There are 2 filled. There's 2 n phi electrons in the system. The filling factor is 2. Okay. So first note that suppose I restrict myself to looking only within the lowest Landau level. And if I make a wave packet within the lowest Landau level, because the dispersion is flat, it's not going to move anywhere. Right? Does everyone see this? So you've learned that if you make a wave packet, its group velocity, and is given by d epsilon dk. Right? So d epsilon dk, if you make a wave packet out of the single particle states, say, these few single particle states versus k, because the dispersion is flat, this wave packet is not going to move anywhere, and this quantity is 0. Okay, so physically, this means you make a bump in real space in the lowest Landau level, it'll just stay put. And what this means is that in the absence of any electric field, the current is just 0. Nothing moves. Electrons are just stationary. Now, this is not surprising because we were trying to explain a signature in the presence of an electric field. So, you'd be really surprised if you had a sample and you didn't apply any voltage on it and you could just magically measure the current, right? So that doesn't happen. Okay, so to see where a non-zero current can come from, we need to incorporate the electric field into our physical description. And so this evening, the tutorial, you're going to solve the Landau level problem in the presence of a uniform electric field. So I'm not going to go through it now. I'll just tell you the answer you're going to find. So it's going to turn out that it's exactly analytically solvable, and the Landau levels now look like this. Okay, so it's the same picture as before, only that the Landau levels are now tilted, and the slope is set by the electric field. Right. Okay. So just a combination of this and that is now going to help us see where we can get this formula from. So notice that the identification between momentum along the y direction and the position in the x direction tells you that the electric field, which is defined as the slope of the potential energy in the x direction, if I identify x with k and v with energy, I find that this quantity is related to xk is minus klb squared, so this minus goes away, and this quantity is just the drift velocity, which is, okay. Yeah.
All the bands have the same slope?
All the bands have the same slope, yeah. Sorry. I know my picture didn't look that way. But they all have the same slope. And in fact, so let me just write down what the slope is. If I plot this versus xk, which is, then I find that the slope is charge times the electric field. Okay, so there's an intimate connection between the current in the y direction, which I get by asking for the group velocity dE dk, where k is the momentum in the y direction, and the slope of this spectrum, which is the electric field, and it's dE dx. Does everyone see this? And this is coming from the fact that basically the position in the x direction is momentum in the y direction, up to the units of the magnetic length. Position in the x direction tells you momentum in the y direction. So asking for the slope of the energy along the x direction, which tells you the electric field, gives you the current in the y direction through this group velocity. And this is the reason one has a relationship like this. Whenever there's an electric field in the x direction, there's automatically a current in the y direction because of this. Okay? And so in your tutorial today, you're going to work out that for each of these eigenfunctions in the Landau level, the current in the y direction is going to be minus E times, well, ECE over B, okay? It's probably an E here. And I can see, and it's right. So this is a result you're going to derive today. You're going to find that the current in the y direction is related to the electric field in the x direction, and this quantity here will then be related to sigma yx, okay? And so I'm not going to do it, and I'm not going to derive it here, but I just wanted to tell you where it's coming from. It's coming from this electric fields in x direction gives rise to group velocities in the y direction. What's that?
This is what we see in experiments in quantum forward effect.
You mean the plateaus?
Yeah, I mean these dependence of sigma x1.
Rated in terms of the approach.
Okay, sorry. So this is the current. Maybe I'll write a small y. This is the current per electron in each of these eigenfunctions. So to actually get the full current due to all the electrons put together, you will then you would derive the formula we wrote yesterday. NEC over B. Yeah. So this is per electron. So in each of these eigenfunctions, then you add them all up for all the electrons in the lowest Landau level. Okay. So I now want to move on to actually introducing disorder and explaining the plateaus. So any questions on this bit? No? Okay. So there's a very general argument based on just Galilean invariance that tells you that this should be the answer, like whether the system was classical, whether the system was quantum, no matter what. So I'm going to go through that now. And it will tell us why, to really explain the full data, this is not enough. We need to actually think about breaking of translation invariance and disorder, random potentials. So. Okay, so argument for sigma xy NEC over B. So I'm now going to give you an argument kind of independent of all this microscopic way of thinking about things, just relying on Galilean invariance. That's going to give you this formula. Okay, so so we imagined that as we did, we started with particles whose kinetic energy is given by p squared over 2m. And then we assert that the system has no preferred frame of reference. Okay, so that a frame of reference in which there is a magnetic field, there is no electric field, and the electrons are at rest, is equivalent to one in which the frame is moving with velocity minus v with respect to its lab frame. The magnetic field is the same, but the electrons are now all moving with velocity v, okay? So if there's Galilean invariance, we know that the physics as described in this frame is the same as the physics as described in this frame. Okay, so in this moving frame, there is a current density because the electrons appear to be moving. And this current density, J vector, is the density of electrons times their charge times their velocity. Okay, this is the areal density of electrons. Okay, further, in this moving frame, for the electrons to be moving, to be able to, so notice that, by the way, I didn't emphasize this. Even though there was a magnetic field here, the reason there was no Lorentz force was because my electrons were at rest. Okay, so here they were just literally static and just at points. Because the Lorentz force is V cross B, it's 0, and Newton's laws are consistent here. In this frame, however, the electrons are moving with some velocity. So that means there is a Lorentz force on them, okay? But for the electron orbits to not become circles like we discussed yesterday, there had better be an induced electric field in this frame, which exactly cancels out the Lorentz force. Okay, and so we derived this, we basically derived the same thing yesterday, and this electric field has to be, let me write it bigger. There is, unlike the lab frame, in the moving frame, there is an electric field induced in the x direction such that the Lorentz force on these moving electrons is exactly canceled. Okay? So in this moving frame, I can now calculate what the conductivity tensor is. So remember, the conductivity tensor was defined like so. Ey, right? And so I know what the current is. I know what the electric field is. So I just plug it into this matrix to see what conductivity tensor I get. And I see that it is 0 times okay? Is everyone with me so far? I can express the electric field in terms of V and B. I know the current in terms of, the same quantities. I just rearrange to find out what the conductivity tensor is. Okay, so, and similarly, I can also find out what the resistivity tensor is, which is just the inverse of this relation. How is the electric field related to the current? And so that's just the inverse of this matrix. And it's B over N E. Okay. By the way, the signs in these matrices just tell you the relationship between the direction of the electric field and the direction of the current. So if a sign is switched, it just means that instead of the current flowing in the plus y direction, when you apply an electric field in the x direction, it flows in the minus y direction. Okay? So it's not negative resistance or negative conductance, nothing fancy like that. Okay, so notice just by using Galilean invariance, which is that physics in two frames that move with constant velocities with respect to one another should be the same, I've derived that the conductivity tensor and the resistivity tensor have these forms always in general. Note, again, classical, quantum, whatever. The only thing that was used here was that I can describe the same physics in two different frames. Okay? Yeah?
When I put an electric field, the velocity of the electrons is small compared to the speed of light, right?
Yeah, there's no radiation. I mean, there's none of all that here, yeah.
What I was thinking is, somehow you're enforcing that there appears an electric field so that the orbits are not circular, right?
Yeah.
But this reminds me of, if I make a Lorentz transformation, how does E and B transform under Lorentz transformation?
Yeah.
What you're doing, but taking then the classical limit, right? Or the non-relativistic limit at the end.
No, I mean, I think I'm using... No, I think it's not, because, see, my charges are not accelerating or anything. They're just moving, right? So I think this is just a Lorentz transformation, like a proper Lorentz transformation of electromagnetic fields. I don't think it's approximate. Like V is not much less than C. That's just, I don't see where I've used it.
But I mean, okay, when you use Galilean invariance, it's just the non-relativistic limit of Lorentz invariance, right?
Oh, I see what you're saying. Okay, yeah, sure. So to the extent that I've the dispersion of the electrons is not relativistic and is p squared over 2m, you can think of it as coming from, yeah. But I was saying more that I've been, given this, and given the Lorentz force, what I've done is exact. But this, indeed, is only, if you wish, a non-relativistic limit of the electrons. Yeah. It probably is.
To what?
Yeah. Oh boy, yes, it is. It is somewhere. Maybe it's up here. It's either up or down.
Well, yeah, it should be it, but I just don't know where it comes from.
Yeah, it will come from the fact that the in writing my Lorentz force, if keeping consistent, my unit should have been minus E over C B cross B. Right? And that clearly has disappeared somewhere. Sorry, there's any C over B? Okay.
Because you've written sigma x, y, z.
Well, that's assuming that was correct, right? No, it's somewhere. B over any C. Let's hope this is where it is. Okay, so
is the electric field in the y direction then?
it's in the x direction.
And the velocity is in the y direction? Okay.
The velocity is in the y direction. So let me, this is y, that's x.
Okay.
So electric field, whatever, yeah, it's in there. It's like E, electric field, velocity, magnetic field. They form a orthogonal set of coordinates. Okay, so notice that we've derived something that's very close to what we want, but it's the classical result. That is to say that the for a fixed density, we find that we have rho xx, rho yy 0. That's good, but the Hall resistivity, which was, remember we said yesterday that in 2-dimension, resistance is the same as resistivity. And so we've derived that this object versus B, just like the classical calculation we did yesterday, is linear with the magnetic field, right? So notice that if classical, quantum, whatever, as long as Galilean invariance is true, I don't have plateaus, right? So I've not explained the quantum Hall effect, despite doing this whole thing about Landau levels, blah, blah, blah yesterday, not explained the quantum Hall effect yet. Why? Well, it turns out that to explain it, we need to break this assumption. We have to go away from Galilean invariance. And the way we do this is we think, okay, in an actual sample, we don't really believe that all frames are equivalent because there's always, yeah.
So in some sense, you are using Newton's laws.
Yeah.
But when you use the Lorentz force, that defies Newton's laws. That contradicts Newton's assumption.
Why?
I think that there's a problem because of the Lorentz force that already defies Newton's third law or something like that. And there's a problem when you do that. I'm reasonably sure about that.
Okay, let's talk about it later. The only ingredients I've used in here is that the force is EV cross B on it. Okay? The reason it's okay for the quantum case as well is that semi-classical wave packets in the quantum problem do the same thing. They feel an effective Lorentz force. They behave as if they're classical particles. And they have circular orbits in the same trajectories as before. So that's the reason this calculation, it's the same for both. But we'll talk about it later. Okay. So what we need is for this assumption to not be true. Okay? And in some sense, this assumption is never true in any real sample, because in any real sample, there is a fixed frame of reference, the lab frame. And what fixes the lab frame is that there is the outside world. And the outside world here is, for example, remember we said that these electrons come from silicon donors? The silicon donors are static. When we do these transformations, this lab frame and so on, the silicon donor was a rest frame. It remained at rest. And so this frame looks different with respect to the silicon donors with respect to this one, and the silicon donors have random positions. So as long as there is a lab frame with fixed positions that defines what our preferred frame is, then we no longer have Galilean invariance, and this argument at least doesn't work. Okay, so we're still left with the task of saying, okay, assuming there's no Galilean invariance, can you explain the plateaus? And so that's what I'm going to do now. But I just wanted to show you that without breaking it, we cannot explain the plateaus. Okay? So let's now break Galilean invariance. So we now want to think about a semi-classical treatment. Okay. So what do I mean by this? Let me write down the Hamiltonian. This is as before, except now I imagine that there is a random landscape, random potential landscape for my electrons that are moving in the presence of a magnetic field. Okay? And it's clear to everyone that the presence of such a random potential landscape breaks Galilean invariance, right? Because in different frames, this potential does not look the same if you shift your frame. So pictorially, we imagine that, say versus x, there's something like that, hills and valleys in my potential landscape. And so some properties of this random landscape, well, on average, there's no potential. Okay, so this is about 0. Let's say that it's actually a random variable whose probability distribution is some given probability distribution independent of the position. Yeah?
I'm not sure if you got in one frame, you got a random potential distribution.
Yeah.
You go to another one with it will still
it's a different, no, but it's a different one, right? So I'm still, this is the statistical properties of my random function. But for every given realization, so there's an average Galilean invariance in that on average, when you make boosts, it looks random, but that's not what I want. That argument that I need is not on average Galilean invariance, tells you, right? I needed it for every single realization of electrons in some potential landscape. Only if I have Galilean invariance for every single kind of potential landscape can I run that previous argument. So I've broken that. I just have it on average, but it doesn't matter. Right? And so the way to really think about it is maybe operationally, I'll tell you how, say you were doing this in a computer, right? And you're trying to solve this Hamiltonian problem. What would you do? What you would do is you're given some statistical properties of your random landscape. But every time you want to solve the problem, you just kind of sample from this distribution. You sample once, so you get some profile like this, plug it in, solve for the Hamiltonian, get all your eigenfunctions. Okay? So you always imagine solving the problem for a particular realization of potential disorder. And then you average over the disorder properties. So, anyway. Okay, so on every site, the probability that the potential has value epsilon is given by this distribution function, rho of epsilon. And this function is smooth, well-behaved, monotonic in epsilon. And let's assume that the total, it's a normalized probability distribution, right? So with the probability that I'll get some value epsilon here between minus infinity and infinity, if I add them all up, it's probability 1. Okay. For epsilon positive, say. Yeah, so, yeah, sorry. Not monotonic for all epsilon. So a good example is the Gaussian distribution for rho of epsilon. Okay. Also, let's imagine that on different sites, the potential is uncorrelated. We're just making these assumptions for simplicity. You can relax them. So the third one is this is 0. Greater than xc, where xc is some kind of length scale, and the potential, I don't know, which tells you like about after this length scale, the potential basically looks uncorrelated. It looks like independent samples from this distribution. And finally and importantly, assume that V of R is varying slowly on the scale of the magnetic length. Okay, so if I just asked what's the variation of this potential V on the scale of the magnetic length, I find that's very, very small. So on this plot, for example, the magnetic length is some tiny scale here. And on this scale, the potential basically looks very smooth and constant. Okay? This assumption, the fourth assumption, that's the reason this is going to be a semi-classical treatment. We're not going to solve the problem exactly. We're going to approximately solve the problem in this limit. Okay, and this is, by the way, identical to the strong field limit, because remember that the magnetic length was proportional to 1 over the square root B. B was a magnetic field. So if I turn up the magnetic field a lot, this length scale is going to go down. And so for any given potential, I can satisfy this. Okay, so this is similar to the strong field limit. Okay, so what can we, now that we've set up what this random potential looks like, how can we solve this problem? What can we say about the eigenfunctions of that Hamiltonian? Okay, so remember that or actually because we've not solved it in class, you'll see today when you do the tutorial that in the presence of an electric field, which is not a random potential, but it's a uniform potential. This is the problem that you'll be solving for today in a tutorial. So in that case, the eigenfunctions that you find would actually be localized on equipotentials of this potential. Okay, so what do I mean? That suppose let me tell you this answer in the simpler case, and then it'll be easier to see what happens for the random one. When v of x versus x was varying linearly, and you were able to solve the problem exactly, what you will find is that the centers of the wave functions, right, the ones that we've been talking about in the Landau gauge, end up being kind of, here. They're equally spaced in the x direction. But importantly for us, it's localized about an equipotential. It's localized about an equipotential for v of x. Okay, does everyone see this? So all I'm trying to say is that if the electron in the presence of a magnetic field, its kinetic energy, which is this piece, we've solved for it. This was the Landau problem. And we said, okay, this piece is basically going to look like n plus half h bar omega c, right? That was the problem we solved for yesterday. So the kinetic energy in the presence of a magnetic field cannot vary continuously. Instead, it's set to values 1/2 h bar omega c, 3/2 h bar omega c, and so on. So once the kinetic energy is quenched, and by quenched we mean that it's fixed to some value, then in order for energy to be conserved, the electron has no choice but to move on equipotential contours of V. Okay? Does everyone see this? So, and you'll find that when you actually solve it exactly for this specific linear potential. But what it means for the random potential is that in the limit that the magnetic field is very, very large, then h bar omega c is a very, very large energy. So this is much, much bigger than the average potential that we have. So this is on average the value of the potential that you have. In that limit, the system is unable to vary its kinetic energy. Because it can't vary its kinetic energy, it can't vary its potential energy, and therefore the eigenfunctions end up being localized on equipotential contours. Okay? So this is these dashed lines that I'm imagining. So this is in the x direction. I'm drawing a 3D plot in the xy plane. And so this, along these dashed lines, v of xy is some constant v naught, and the eigenfunction is delocalized along this line, but very, very localized along the gradient of the potential energy. Okay, so in this approximation, we can write down what the wave function looks like. And we write it down treating kind of this direction as the y direction in our Landau gauge, the delocalized direction. and this x direction. So this, locally speaking, from yesterday's problem, this direction is x, and this along the contour is y. Okay, so it's like at every point here I have a mini Landau level problem in which along this direction the potential is a constant. That's what is my y from before. X is the direction in which the potential is actually changing. And so I can write down approximate wave functions. Let's call these actually primes so it's not confusing. Prime. Prime is 0. Some phase. Okay, so all I've done is, this is up to a normalization factor here. This is basically the Landau level wave function I had yesterday. And here is the Landau level index. X prime plays the role of x. It's the direction, this direction. The phase, which is proportional to y, is in here. And this is a normalization. Okay? Yeah. Yeah.
What do you mean by the square root of a gradient?
Sorry, the gradient is along this direction, right?
Okay, the x component.
X component of the gradient, sorry. I mean, there's probably also a mod in here. It's not, yeah. Okay. And so this wave function has approximate energy. Plus V, where V is the value of the potential on, basically at x prime is 0. Right? So when I've defined coordinates such that locally x prime is 0 is on the equipotential contour. So this guy is just some constant u. It's independent of y prime by definition. And then this is the wave function. That's the energy. Okay? Okay. So so we don't know how to solve the problem exactly. However, we have some approximate picture based on our Landau level intuition for what we think the eigenfunctions look like in this random potential. Okay? And the picture being that it's always localized on equipotential contours. So this picture is enough for us to actually have provide some kind of full solution to this problem. So why is that? Why is that? That's because this problem maps to another problem in statistical mechanics that's well studied, which is known as percolation. Okay? Okay, so what is percolation? Percolation is, in percolation, the problem is as follows. You say you have a random landscape, and you imagine filling water into this landscape. Okay? So what you tune is the water level. So let's do that first and just ask what we'd see. So if we started filling this landscape with water, when you put in very little water, first we would just have very, very deep valleys filled with water, right? We then, to map our problem to this water problem, that the language I'm going to be using for the rest of the class, we realized that the boundaries of these puddles that we're creating by filling water will be our eigenfunctions at the energy E that we talked about. Okay, so water level is energy. I fill valleys with water, and the boundaries of the puddles that I create will look like the energy eigenfunctions at E for my electrons in disorder potential problem. Is this analogy clear? Yes? Okay. It's exactly this. It's just if you fill this thing up with water till here, right? There is a boundary between empty and full, which is basically it's an equipotential, right?
Circle.
Yeah, just a circle.
That's your eigenfunction?
That's my eigenfunction, yeah. Yeah, because my eigenfunction is stuck to equipotentials, yeah.
About this picture, because I expect if I solve some 2D potential, that the time-independent solutions will be, like the eigenfunctions at least will be localized more or less to the minimum of that potential. So what did you mean when, like in this case, it's obvious that the wave functions would move around only on the equipotentials of my constant line, because those are just circles.
Yeah, but
In this case, what did you mean? Like I could have minima that end at some point in my 2D picture of my potentials. So I'm not sure what the picture is exactly. You mind explaining it?
ask your question again.
So what did you mean by wave functions move on the equipotentials of this 2D?
I think it's exactly as you understood it, which is that the wave functions move on equipotentials, and when I fill water up to some level, I define an equipotential. That's all I'm saying, right? So water level is the potential up to which I fill, but that's defines an equipotential, and therefore an associated eigenfunction for my quantum problem. Okay? So there are two easy limits in this water filling analogy. The first is when the water level is very, very low. That's the picture here. And that corresponds to various energies. So actually, let me move this up. So when so remember this is small e is my energy of the eigenfunction. And I'm actually, capital E is the energy of the eigenfunction. And let me subtract out the piece due to the Landau level, okay? So this piece is the kinetic energy part. So what's left here, small e, is basically just due to the potential energy part. And this is going to define the equipotentials in my potential landscape. So first, when small e is much, much less than 0, that's the picture we drew up there. And we have that the states are localized in valleys. Okay, so the opposite limit, that's also easy because now the states are localized around hills, right? So does everyone see that? If I have we'll just draw a small part of the potential, one hill, one valley. This is a hill, that's a valley. This is my potential. Say this is 0 for small e. And so when e is much, much less than 0, my states looked like this. They encircled the bottoms of the potential. Whereas when my e is much, much greater than 0, they look like this. They encircle the tops. Okay? So in both cases, I have pretty small circular orbits that encircle like bottoms or tops. That's what my eigenfunctions look like. At intermediate energies, you actually see something interesting happens, particularly at energy 0. That's exactly at this energy. What happens is as you increase the water level from here all the way up to there, you see that the these boundaries to the puddles, you could call them the shoreline. This shoreline percolates from one side of the sample to the other. Okay, so instead of drawing this picture, which is kind of three-dimensional, let me draw the view from the top of the eigenfunction. So for energy E less than 0, the eigenfunctions look like this, and they're encircling the bottoms of this potential. Okay, so they look like that. In my filling analogy, I have filled the water in here. Now at energy closer to 0, what happens is these puddles become bigger. Now they start to look like that. Maybe one has even done this. So again, this is filled in my analogy to puddles. This is energy tends to say 0 minus. And notice now what I mean by a shoreline percolating. For this big puddle, this is the shoreline. This is what defines, remember, my eigenfunction at this energy. And you see that it's now delocalized over the entire length of the sample. Right? So this is in the water analogy, this is known as percolation, because if you put in water here, you can now get it out here. Whereas before, if you put in water here, there was no way to get it out here. Right? So once the water percolates from this side to that, the corresponding eigenfunctions, which are stuck to the edges of these puddles, also are delocalized and make it from one side to the other. And in the opposite side, when the energy is bigger than 0, what happens is that most of the landscape is filled with water, but the shoreline, which now encircles the tops of mountains or hills, so this is now all filled with water, still doesn't percolate from top to bottom, right? So the question of interest to us is, does the shoreline percolate? Is there a shoreline from top to bottom? And we see that when the energy is bigger than 0, when there's too much water, no, there's not, the shoreline is stuck here. Too little water, no, there's not, shoreline stuck here. Just in between, not so surprisingly, which is like here, that's where the shoreline is able to make it through a lot of the system, and our eigenstates are delocalized over the size of the system. Okay? Okay, so this is a nice picture, and how does this help us explain the quantum Hall effect, which is what we want to do. So the first thing to notice is that when these eigenstates are localized about valleys or about hills, that they effectively correspond to insulating states. Okay, so both here and there, sigma xx is 0. Okay, so why do we say that? Well, let's imagine now that we add an electric field in the x direction. So this is the x direction, and I add a little electric field. When we add an electric field in the x direction, what we can do perturbation theory in the basis that we've defined without the electric field, which is these guys. So what I do is I pick the few eigenfunctions here of a few different energies. Okay, and then the electric field is going to slightly perturb each of these wave functions and mix them a little bit. But what you'll find when you do perturbation theory is that it only mixes a finite number of these eigenfunctions, and that the shoreline never percolates. Okay, so Is this making sense? What I'm trying to argue to you is that when the eigenfunctions at some energy E, which is lesser than 0, so they look like they're localized about valleys, then on adding an electric field, they're perturbed only slightly. So instead of looking like this, instead of this one looking like this, maybe its shape changes a little bit. But what does not change is the fact that the shoreline percolates from one side to the other. So the electric field cannot cause the shoreline to percolate from one side to the other if it wasn't doing so already. So that means the electric field is just a minute perturbation to this. Without the shoreline percolating, there cannot be transport in the system, because remember, what the shoreline means to us is that there is an electronic eigenfunction that gets from here to there. If there's an eigenfunction that gets from here to there, you can transport charge from here to there. Without this eigenfunction, you can't, so these guys are all stuck, and this is an insulator. Okay? Same argument here. Even though the full landscape is filled with water, doesn't matter. Shoreline is stuck to hills, so when you turn on a little electric field, this just deforms their shapes a little bit. Cannot cause them to percolate from one side. Cannot cause the shoreline to percolate from one side to the other. Cannot result in transport of charge. So this is also an insulator. Okay? So you notice then that what we've developed is maybe a picture of the one quantum Hall plateau to another, and this is going to be our transition between the two. Right? So does everyone see why this is going to result in a plateau? Because I have an entire range of energies, which as you imagine filling up this landscape for these eigenfunctions, that's like changing your chemical potential. The water level corresponds to chemical potential. And you see that for a large range of energies, the shoreline never percolates. So sigma xx will remain 0 for an entire, if I think about changing the chemical potential in this problem, and chemical potential corresponds to how many of these eigenfunctions do I fill, you see that when the 0 is special, when the chemical potential is really negative, I'll fill a few of these guys. Sigma xx will be 0. When I increase the chemical potential by a little bit, I'll fill a few more of these guys. Maybe I'll fill some around here. The argument for percolation doesn't change. Sigma xx remains 0, remains 0, remains 0, until something special happens here. It actually spikes, as you'll see. And then on the other side, when the pictures look like this, once again, sigma xx is 0. Okay? Yeah? Yeah, so these actually look just like the classical orbitals in the presence of a magnetic field. So there's a direction in which the electrons move, which is set by like the direction of the magnetic field. Yeah, like this one. So this now corresponds to electrons moving all the way from here to there, whereas these only correspond to them making little circles in the sample. And making little circles in the sample, even when I apply an electric field, just perturbs them by a little, perturbs where these circles are by a little bit, but doesn't cause an electron to move from one part of the sample to another. So that's right. There is still well, it's more like there is local magnetization, if you thought. It's not that there's a local current. So if I took if I took a slice of the sample like this, the net current is 0, right? Because there are as many electrons moving this way as moving back, right? So whereas here, if I took a cut, it's non-zero. Right? So it's not that there's a net current here. Sure, electrons move in little circles, so there's little current loops, but that's not net current. Yeah? This one?
Yeah, because like in real data, it's actually quite wide.
Yeah, yeah.
So what explains that?
So here, let me draw. Actually, let me plot it a little bit better. So what I'm plotting is actually, as you said, this is, say, chemical potential versus sigma xx. I find that it's 0 special, it's 0 on this side, 0 on the other side, and there's a peak here. Now, okay, so what determines this peak is temperature. So as temperature becomes greater, this peak will get smoother. And then there's, so then actually I'm not entirely sure what the status of this is. There's supposed to be, there's a claim that there's a universal value of this sigma xx exactly at the transition. I don't know if this has been confirmed experimentally. Yeah, so what sets this height is supposed to be something universal. I don't know if it's been confirmed or if everyone even agrees what the value is. What sets the width is usually temperature.
One other thing is there's no with this water picture is like if these hills are narrow,
Yeah.
the minimum energy I need to be in them is much higher than the minimum of my hill. So that's completely ignored here.
If my hills are narrow,
But even
you mean valleys?
yeah, sorry, that's what I
Okay.
the bottom of even though the bottom of the valley is really low, the minimum energy I need is like way up here. So it's narrow. So are we just saying like
No, so if the bottom of the valley is like this, right? I could start from here, I could fill it up till here. Yeah, I can, so think yeah. So sure, there is a quantization that I didn't talk about for these, is that's what you mean, right? I can't continuously change the energy level. And indeed, so the correct analogy is that the water level height is like a chemical potential, which you can change continuously. But electrons will jump in discretely. So when I change the chemical potential from here to there, okay, there'll just be one electron, pop, one more electron will come in. I'll change it continuously, one more will come in. So the electrons will come in, or the density will change only discretely when I change the chemical potential. So that's the correct analogy. Chemical potential is like water level height. Indeed, there is some finite spacing between these energy levels, and so the density won't change continuously right near the bottom. But near here, right, where we want to understand this transition, that doesn't matter so much. There's okay, so hopefully you see how the how this picture of disorder helps explain the width of the plateau. We've not yet explained sigma xy. We'll come to that in a second. But at least we have tried to argue that sigma xx for a finite range in chemical potential. So imagine this chemical potential, by the way, starting from here to there, this 0 here will correspond to a fully filled Landau level. So this corresponds to 1 electron per flux quantum. Oh, sorry, no, that's the opposite. The transition is it's in between Landau levels. So the transition is actually here. It occurs at the center of a Landau level. So as I increase the chemical potential really negative, there are no electrons in the sense system. Chemical potential really positive, all the states are filled, and this is a fully filled Landau level. And exactly in the middle, half-filled Landau level, there's a transition, okay? So at least by drawing this and by saying that the picture looks like this or that to either side of the transition, we have tried to motivate how a plateau will come about. Everywhere to the left of this half-filled Landau level, the eigenstates look localized. They're not perturbed by the electric field, and they don't carry a current from one side of the sample to the other, and so there's a plateau, right? Exactly at half the transition, something dramatic happens. It does percolate. The system is no longer an insulator. It is dissipative. That's why sigma xx goes up. And then on the other side, above half filling of the Landau level, same picture, only we place valleys by hills. Yeah?
You mean in this context, half-field Landau level, we're just considering a one-particle Hamiltonian?
Well, so half-fill Landau level is more this counting of number of electrons divided by number of flux quanta. So I can still define this object. Number of flux quanta defined by magnetic field, just number of electrons. So this, when this was 1 in my clean picture, that used to correspond to fully filled Landau level. So all I'm saying is the transition here is when this guy is half, which is to say there are exactly half as many electrons as there are flux quanta. Okay, but yeah, so I'm using the language of Landau levels despite there being no Landau levels here. And all I want to say is that the degeneracy of a Landau level sets for me how many states I have to fill. And that's driven in the disorder problem. Okay, so now let's see how, so this is sigma xx. Let's see how sigma xy is non-zero and also has plateaus. Okay, so to do that, I need to draw my picture for E greater than 0 a bit more carefully. A picture there. So when I have edges on the sample, right, B versus X, in the bulk of the sample, it still looks like this. However, an edge of a sample basically means that there is a huge confining potential that defines, roughly speaking, the length of the sample. Okay? So, so this is how I would, in this language of the potential landscape, you can think about edges. Edges is where the potential just shoots up so that it confines the sample to be within some width, say Lx. Okay, so how does the presence of these edges affect what we've said so far? So for E less than 0, we see it doesn't really matter because for E less than 0, or the chemical potential less than 0, we said that the eigenfunctions encircled valleys. And sure, now there might be some valleys near the edge of the sample, but so what, okay? So this picture doesn't really change. And you see that not only sigma xx 0, actually sigma xy is also 0. There's just no conductivity or the system, no matter which direction you apply the potential and try to measure current, there's no current because no electron is actually percolated through the system. Okay, but look at how the picture changes for E greater than 0, or chemical potential mu greater than 0. Okay, so now remember what the difference is, that we've gone above 0 is around here. Small e is now positive. So indeed, like we said before, we would encircle hills. But now there's also going to be one state which is localized on the edge, right? This is where my energy level hits the edge of the sample. And so in addition to what we drew before, which is these guys that encircle hills, we see that we also have this. Does everyone see this? Edges naturally create for me these shorelines that percolate through the sample when the chemical potential is bigger than 0, so that I have more than half an electron per flux quantum. Okay, and as was pointed out, these electrons actually, there's a direction in which they move. So these edges actually are oppositely moving electron channels. So the electron on this edge has one direction, the other one has the opposite direction, and it's these oppositely moving electrons that give rise to the sigma xy, which is, I think that was what we said, right? NEC over B, which is EC over B here. Okay, so does everyone see this? This is a quantized sigma xy. It's independent of the value of E or mu as long as E and mu are bigger than 0. And where it's coming from is the fact that no matter what this value is and it's bigger than 0, there's always going to be one electron that's going to percolate, come from top to bottom here, the other one there. So that now when I apply a voltage between these two in this direction, what a voltage does is it tells you that there are more electrons in one of these guys than this one. So if I apply a positive voltage here, a negative voltage there, electrons are attracted to positive voltage because they have negative charge. So there are more electrons here than there. And so there will be more electrons coming from top to bottom than going up. And I'll have a current in the y direction. Right? So this is the quantized Hall response. I applied a potential and electric field in the x direction. I have electrons that move transverse to that potential. So by applying a voltage, I have more electrons moving one way than another, and so I get a current in the y direction, and I get sigma xy. Yes? So while sigma xx is still 0, because when I apply voltage in this direction, I still don't have anybody percolating in the x direction. Yeah? Why don't they go away? They don't go all the way around. Oh, okay. So in this picture, I've only imagined that I'm working on a cylinder. So like we did yesterday for the Landau levels. So in the y direction, they just go around this way, and only in the x direction do they have this steep confining potential. Okay? So they would go around all the way. If instead of making something like this, suppose I made a circular droplet, they would go around all the way. If I had a circular droplet, it would go. It's just I didn't put a confining potential in this direction. I just put it in this direction, so it's periodically going around the other one. No, the physics is the same even in this sample versus that. It's just I have to describe the way you do the experiment more correctly between the two. The physics is still the same. In this one, when you apply a potential to, what you do is, just to tell you, in the circular samples, what happens is that when you apply a potential, you do a 4-terminal measurement. So you apply the potential here, plus V, minus V, and you measure the current along here. So this edge is actually broken up. Is that right? So think of these are literally electrons moving around these lines. So by attaching 4 leads, you put a potential here, but you break the edge because you measure the current. And so then it starts to be similar to this. Okay, so these are the plateaus. So we have now explained at least one this is at the okay, so this is I hope I've shown you that this is the kind of plot you're going to get by varying the chemical potential on a picture like that. There's a jump in Rxy, which is related to sigma xy inverse. I say dimensionless here because it's measured in units, I think, of h over e square or something. So multiplied by the correct quantum of resistance, and this is a dimensionless number, and it's going to jump from 0 to 1. And this 1 is the quantum Hall effect. This is the integer quantum Hall effect, the fact that this is an integer, and this is quantized to 1 part in 10 to the 10 for an entire range in chemical potential, okay? At the same time, Rxx is 0 here, jumps here, and is 0 here again. And right here is, this point is there's a phase transition between an insulator that's trivial and an insulator that's, it turns out, is topological. But, so there's two different kinds of insulators, and there's a phase transition between them. And this picture of percolation, I'll end with that. This picture of percolation actually gives you a theory of this phase transition, and makes some predictions that have been tried to measure experimentally. So particularly, what it says is that as you approach this transition, so let me normalize this to, this is E is 0, this point here. So as you approach this transition from the left, we said that these puddles have a growing size. So from percolation theory, the characteristic size of this puddle is known to grow as mod e to the power minus 4/3, okay? So, and what the meaning of this characteristic size is that the puddles of size bigger than psi, so those puddles with size L much, much bigger than psi are exponentially rare. Or, which is to say that they basically never occur, so this psi gives you a scale beyond which there are barely any puddles of bigger size. So translated to the quantum Hall problem, it tells you that there is a correlation length in the system. So you've all done StatMech and you've seen some phase transition before, right? So you know that a critical point is characterized by a number of critical exponents. One particular critical exponent is given by how the correlation length, which is this psi, grows as you approach the critical point. So our critical point is controlled by, say, the chemical potential. And translating this to that, we find that the correlation length, which is about the size of our eigenfunctions, diverges as we approach the critical point with a correlation length exponent predicted from percolation. This is even an analytic result to be 4/3. Okay? How would this turn up in a measurement? So that plot there, or let me actually keep it at Rxy. That plot there said that at 0 temperature, there is a jump. Now, at finite temperatures, this jump is rounded off. It's actually a smooth crossover. So as you increase the temperature, this jump becomes smoother and smoother. It's more like a crossover from 0 to 1. And so the way you would measure this exponent predicted from theory is that you would actually try to do, there's a scaling form for the resistance Rxy as a function of mu and t, which is that it's h over e squared times some function of t psi. Okay? So what does this mean? This means this psi depends on mu. So what this means is that if you rescale all these plots such that Rxy is measured in units of h over e squared, And mu, you don't plot mu, but you plot this particular combination, which is t times mu minus mu c to the minus nu, okay? So just rescale your plot. Don't plot with this mu. Plot with this t times mu minus mu c to the power minus nu. Nu is given its number. All these plots will fall on top of one another. That's what a scaling analysis tells you, okay? So this is a way in which you could, and they've tried to measure this exponent experimentally. Just repeat your experiment at different temperatures, get different curves for the RXY resistance versus mu or actual magnetic field. Rescale your axes. All the curves will hopefully fall together if you have the correct value of mu. Okay, so this is, I think you've seen scaling before in the StatMech course. Hopefully this gives you an idea of how you can measure scaling in an experiment. You usually try to measure a scaling function that you would calculate theoretically by collapsing plots. Yeah.
You just showed with this analysis an analogy with calculation that your whole conductance is just, means not quantized, it's just 1 times the fundamental unit.
Yeah.
Right? But how would you explain the fact that it's quantized just in integer value that I can have 2 times that or 3 times that?
So in everything I've just talked about, I somehow assumed that we were only working in the lowest Landau level. If instead we worked in the second Landau level, it would be quantized to 2. Third Landau level, 3.
If I kind of extrapolate this graph, then I'll find that, for example, when mu equals 3 halves or something else.
Yes, that's right. That's right. That's right. It jumps exactly in steps spaced equally with what do we write that? Mu n star is n plus half h bar omega c. Yeah, so half, 3 halves, 5 halves, 7 halves. Yeah.
Another thing, we're neglecting at all every interaction between
Yes. And that's right. Why is this justified?
Yeah, why is this successful if it's not highly correlated?
Okay, so tomorrow we will not neglect it. The reason it's successful for what we're explaining right now is that the energy scale between Landau levels, which is what we're thinking about, is h bar omega c. Whereas the interaction scale, so remember this analysis we did, let me move here. So remember how we understood how interactions have strength divided on this thing? Okay, so the interaction scale as before is set by the magnetic length, E square of LB. However, kinetic energy, instead of being like P square over 2m, is actually set by Landau level spacing. So at really big magnetic fields, this scales, I think, as 1 over square root magnetic field. So when our magnetic field is very strong, which is where all this data is taken, this ratio is really small. So we can actually forget about the interactions when we're trying to explain the integer quantum Hall effect, because the integer quantum Hall effect, the relevant energy scale between different Landau levels is h bar omega c. Tomorrow, when we do the fractional quantum Hall effect, we'll find that the kinetic energy is the same for all these different states that we want to talk about, because we're going to fractionally fill a Landau level. And so then the denominator is 0. And this is infinite, and interactions is everything. So, but for integer, the denominator is set by Landau level spacing, and that's huge. So we can forget about interactions.
Why doesn't this analysis apply to the fractional quantum velocity? Except, I know by this reason you can use it, but when you consider in the fractional case, you don't introduce a potential that models disorder.
No. So experimentally, it's seen that with disorder, the fractional quantum Hall effect is destroyed. So it's, as far as we can tell, it's some physics to do with very, very clean systems. Even a little bit of disorder, the integer plateaus persist. They're very robust. Tomorrow we'll see, right, that there are actually fractional plateaus at fractional fillings. Okay, you know what I mean. There'll be extra plateaus in here. These go away. So as far as we can tell, disorder destroys the physics for the fractional one. And that we understand theoretically, whereas
And you said before that even if I don't have disorder, there's still plateaus for energy value.
no, if you don't have disorder, there's no plateaus in energy value. You'll get a linear curve. To get plateaus, you need disorder. Yeah. Without disorder, you do still have the edge, yeah.
So why is there no plateau?
Oh no, so there's no plateau because there's without. So I'll give you another picture that might make sense. So one thing I can plot is the density of states. So it's density of states versus energy. So in the clean problem, right, I had my density of states looked like delta functions. There were n phi states where n phi was the degeneracy of each Landau level at like half h bar omega c and so on. So these are the Landau levels. They were highly degenerate, and there was nothing in between, right? So without the disorder, the reason you cannot explain the plateaus is that whenever you imagine trying to change the number of electrons in this picture, right? So say you have like n over n phi. When we change this chemical potential mu, what we're changing is the number of electrons in the system, n. So you notice this, as I try to vary n, I have like, okay, I don't know, I occupy some number of levels here, more, and then it pops to the next Landau level and so on. So the only place I can explain using the clean edges, the sigma xy result, is for fully filled Landau levels. When n over n phi is exactly an integer, then in the clean system, you can explain how sigma xy is equal to nu e square over h. Okay? Just 1 second. So without disorder, another way to say it is that disorder pins the chemical potential to lie exactly at the Landau levels. You cannot change the density of the system continuously, because as soon as the energy is here, suddenly you populate the entire Landau level. And you go here, suddenly you populate the entire Landau level. What disorder does is it smears out this density of states such that except at the center here, everything below the center, these are all localized states, which were of the picture that we drew. So basically, what disorder does is it fills in the density of states with localized states that don't change your conductance properties, so that when you change your chemical potential continuously, every time you hit the center here, that's when you go from no edge states to one edge state to two edge states, 2 to 3, and so on. Okay, so maybe I should say this after class. There's no way to with the clean system, there's no way to meaningfully even think about the plateaus, because you cannot change the chemical potential continuously. You need like extra density of states. No, there's no plateaus. There's just the response at points on this. So without disorder, I can only derive the response at like points in this graph. I can't derive it there are no plateaus without disorder. For plateaus, you need disorder. Yeah. Okay. Thanks. I'll continue tomorrow.